Hello, hello. We are going to take some notes on 4.7, inverse trig functions. So of course, before we talk about what inverse trig functions are, what they do, let's see what we remember about inverses. Maybe if you want to pause the video and brainstorm for yourself, that would be a great idea. Otherwise, a couple things we hopefully remember about inverses. They are reflections over the line y equals x. What else do we remember? If we want to find an inverse, we are going to swap x and y, and then solve for y. And then remember we renamed it f inverse of x. This means inverse. What else do we remember? If we want to figure out if a function has an inverse, we are going to look at the horizontal line test to determine if a function has an inverse, f inverse of x. So those are, oh, and then the other big important thing we maybe remember is that when we compose a function with its inverse, we are left with just x, and we can compose the other direction as well. F inverse composed with f of x is just equal to x. So these are all the general things hopefully we remember about inverse functions. And let's take this information a little further. Oh, that is not what I want to do. I want to look at the horizontal line test for a moment, because that one is going to be kind of important for what we are about to see. Sorry, I kind of went a little crazy there. Okay, so the question we were just about to answer is, how do we know if a function has an inverse? And one way to decide is with that horizontal line test. So remember, like if this is our function, it's some parabola. If I can draw a horizontal line through it and it hits the graph twice, that does not pass the horizontal line test, this function will not have an inverse. Specifically an inverse that is also a function, right? Because if I took this thing and reflected it over that line y equals x, the reflection would look something like this. And this guy, the green graph, is not a function because it does not pass the horizontal line test, right? So now the question we have to ask is, does sine have an inverse function? And if we consider, I don't want that yellow. If we consider the graph of sine, which I know looks like this, does this function have an inverse? Hopefully you're thinking, well, no, it doesn't, right? I can draw a horizontal line and it hits the graph technically an infinite number of times. So maybe you're thinking, well, why are we even doing this lesson? And so we do actually have an inverse sine function. We just can't basically use the whole function. Essentially, I need to say, I'm not going to look at this entire curve. I am only going to look at a little piece of it. I am going to restrict the domain of sine to only go from negative pi over 2 to positive pi over 2. So let me kind of re-explain what I'm saying. Here is the graph of sine. It goes on forever and ever in both directions. I know that the period is 2 pi, which means this over here is negative 2 pi. And if I look at this entire curve, I cannot have an inverse. But if I only look at a piece of it, specifically this little part right here, from pi over 2 to negative pi over 2. If I say we are going to cut this graph, we are going to ignore everything else and only focus on this piece, then sine does have an inverse because it passes the horizontal line test from negative pi over 2 to positive pi over 2. this is what we do. We are going to restrict the domain of our trig functions so that they do have an inverse on a certain range. These restrictions, pi over 2 to negative pi over 2, that is something that has been decided. It isn't something I just picked. It's something that the math world is in agreement on. So inverse sine functions. Let's talk a little bit more about what that is, what that means. For a moment, I'm going to consider the function just normal sine of x. This is our OG function, right? And in this, I put into it some angle measure. And my output, what I get out, is the sine value at that angle. What do I mean by this? Well, sine of pi over 4 is equal to the square root of 2 over 2. This is an angle measure. This is a sine value, right? That's what we have been working with on our unit circle. Sine of pi over 4, sine is y, is square root of 2 over 2. And this is great, and this is lovely. In inverse sine, well, we remember sine inverse of x is equal to y. Remember, inverse functions switch x and y. So instead of x here being an angle measure, x here is actually a sine value, and the output, the y value here, is the angle measure. We switch x and y. So instead of sine of pi over 4, I would be asked sine inverse of square root of 2 over 2. That would be equal to pi over 4. Basically, inverse functions are saying, where is sine equal to this thing? Where is sine equal to the square root of 2 over 2? And we would answer with, oh, it's at pi over 4. But wait, there's another place on our unit circle where sine is equal to the square root of 2 over 2. That's at 3 pi over 4. So why did I say this was our answer when there's another angle here? And that comes back to our restriction. Remember, inverse sine is restricted from negative pi over 2 to positive pi over 2, which if we look at our unit circle, pi over 2 is right here, negative pi over 2 is right here. Inverse sine only lives on the right half of the unit circle. It can only be defined from pi over 2 to negative pi over 2. So this angle, 3 pi over 4, well, that won't be a solution because it is bigger than pi over 2 right here. Let's see how this plays out in our other trig functions. For cosine, we're going to have the same issue again, right? Cosine, that was not a very good cosine graph. Cosine looks like this, but we can't have the entire graph of cosine, and so the restriction for cosine is from 0 to pi. Cosine inverse only lives on the interval from 0 to pi. If you think about our unit circle, 0 is right here, pi is over here. Cosine inverse only exists on that interval in the upper half. We are going to restrict our domain from 0 to pi. And inverse tangent is actually kind of an interesting one. So let's remind ourselves of what the graph of tangent looks like. I know that it has asymptotes. Oh, those are bad asymptotes. And it generally looks like this. My asymptotes are at pi over 2 and negative pi over 2. And so tangent is actually one of the easier ones. Tangent just gets restricted in its first period, basically, from negative pi over 2 to positive pi over 2. Just like sine, inverse tangent lives on the right half of our unit circle. One other thing to mention about these graphs is, I've been writing tangent inverse of x. Another way that inverse functions in trig are sometimes written is this phrase arc tangent. So that means inverse tangent. These two things are the same. Or I would be saying the same thing for sine inverse of x is the same as arc sine of x, or cosine inverse of x is the same as arc cosine of x. It's really just a different notation. So if you see this, it's just saying, hey, this is the inverse of that thing. The last little bit I want to talk about is just to reiterate again what's happening here and remind ourselves of some domain and range things. So the graph of sine, the original graph, has a domain of all real numbers and a range from -1 to 1. The domain and range of cosine, -infinity to +infinity, and -1 to 1. And then the domain of tangent is a little bit more tricky, right? That it's everything except those asymptotes here. And so I'm not going to really write that. I'll just write all reals except the asymptotes. So pi over 2, that would mean -pi over 2, etc. And then the range here, the range is actually easy, from -infinity to +infinity. These are, again, domain range of the original functions, not the inverses. If we consider the inverse functions, for sine inverse is restricted from pi over 2 to -pi over 2. And here's where things get interesting. This little blue curve is actually not inverse sine. Remember, because we reflect it over the line, y equals x. So inverse sine actually kind of looks like this little purple thing right there. That's sine inverse. And the domain and the range are flip-flopped with the original function, right? Because if an inverse function switches x and y, and domain and range are x and y, then they have to be flipped. Now, that means the domain of sine inverse is the range of sine, -1 to 1. And this is where we have to restrict. So the domain of the original function gets restricted to -pi over 2 to +pi over 2. And that domain restriction becomes the range of this function. For cosine, it's the exact same idea, except for instead of from -pi over 2 to +pi over 2, we restrict the domain from 0 to pi, which means for cosine inverse, the domain, again, is the range of the original, so -1 to 1, and the range would be, from 0 to pi. And then for tangent, we keep one period. For tangent inverse, the domain is the range of the original, -infinity to +infinity, and the range is the restricted domain, so from -pi over 2 to +pi over 2. Those are our notes for 4-7, and I said we're going to take just like 30 seconds of notes on 4-8, and really the only thing that I need to define for you here in 4.8 is what it means to be an angle of depression or an angle of elevation, because those will come up. So an angle of depression versus an angle of elevation. And to show these, I'm going to draw a really quick picture. So let's say we have a plane up in the sky. Not a very good one, but that's okay. And we've got a person down on the ground looking up at that plane. The angle of, well, I actually flipped these. Sorry, I'm going to switch. There we go. Okay, angle of elevation would be from his eyesight up to the plane, and an angle of depression would be like the plane's eyesight, I guess, down to that person. So angle of depression, you are starting at a horizontal and basically opening down to get that angle. An angle of elevation, starting at some horizontal and opening up to get to that angle. That is the only thing I need to tell you for 4.8. I hope you have a lovely rest of your weekend.